Ahora vamos a escuchar al profesor Ramiro Lafuente de South Dakota University, de Estados Unidos, que nos va a hablar sobre una visión reticular de la topología.
Muy bien, muchas gracias. Bueno, las buenas noticias son que voy a dar toda la charla está muy bien explicada en español y lo he hecho lo más grande posible para que puedan leerla. Sin embargo, como tenemos un invitado muy especial, el doctor Cantrell de la Universidad de Miami, que no habla español, entonces yo les pido disculpas por la consideración que le tengo al profesor Cantrell. Voy a hacer la charla en inglés y voy a apuntar todo lo que diga que está escrito en español, exactamente lo mismo. Así todos van a poder entender mi charla. Okay, so my talk is about reticular perspective of the topology. This happened well. They started to talk about topology without points in the early 1900s. But this is not exactly topology without points. However, this is based on lattices. Okay, so what is my goal? We consider lattice L, on which I will define a topology called the prime spectrum of F for the lattice L. And this topology is called the whole kernel topology. I will establish some definitions, and at the end, I will state some properties of this spatial topology that can be generalized in the totality. Okay, so let's start with this. That is a lattice that satisfies. This is the very basic definition of lattices: idempotency, associativity, commutativity, and absorption law. And on top of that, I will add the fact that L is distributive. That is important. Okay, but because not all lattices are distributive, as you know. All right. We can also define a lattice using a partially ordered set, in which we define the infimum, and we will call this A infimum B, or A, or the meet of A and B as the usual infimum of A and B. That is the greatest lower bound, right? And the same for the supremum. We will say that L is complete if the supremum and the infimum of an arbitrary family exist in L. So in other words, this can be infinite. And because we said for arbitrary, the infimum of the empty set and the supremum of the empty set by vacuity is 1 and 0. We will call them, they exist by vacuity, and we will call them 0 and 1. So 1 is the top element and 0 is the bottom one. Okay, I'm very concerned about prime elements, very important. So a prime is a non-bottom element P in a lattice L if this condition happens. That is, if the X infimum Y is less than or equal to P, then X is less than or equal to P, or Y is less than or equal to P. This is a general definition. However, when we have a distributive lattice, This condition is equivalent to this one, that sometimes is easy to handle. All right. We know what's a prime number, a prime element. We denote the set of all primes of the lattice L by spec of L, and it's called the prime spectrum of L. Now, from this point on, it's not like I'm mimicking, well, loosely speaking, I would say that it's like a mimicking of translating some topological concepts into lattice concepts. For example, what is a compact element? We know that in topology, a compact set is something for which, when we have an arbitrary open cover, we have a finite subcover. But in lattice theory, we define it this way. So L is compact if whenever C is less than or equal to an arbitrary infimum, then there is a finite number of elements in the index set for which C is less than or equal to that. So this is the finite cover for C, for the compact C. And we will denote the set of all compact elements by K of L. K of L, compact elements. What's a frame? A frame is a complete lattice, so infimums and supremums of arbitrary sets exist, and with one particular property. This property is a stronger distributivity property, this one. About, I would say, middle of the 1900s, Brouwer was the first one that talked about this property. And they used to call this the Brouwerian lattices, but later on, with the work of Banachevsky and McGovern, they call it just frames because of the topological aspect of this theory. Okay, and of course, if this stronger distributive property works or is true, then in particular, the lattice is distributed. All right. Here we have two examples. The first one is maybe not so important at this point. Later, you will see that it is important. All Boolean algebras are frames. All Boolean algebras are frames. Complete Boolean algebras. The power set, I have another example that maybe I should write down. If A is a set, the power set of A, the set of all subsets, el conjunto de partes, with this, or if you want, with the intersection as the infimum and the union as the infimum, is also a frame. Es también un marco. The second one, example 2, is a very important one. You know what's a topological space. I will just review it. Topological space, and let me say this in Spanish. Recordemos que un espacio topológico X tau es un conjunto X y tau es un subconjunto de las partes de X, donde están X mismo, el vacío, es cerrado con respecto a la intersección de un número finito de abiertos, les llamamos abiertos a los elementos de tau, y la unión arbitraria de abiertos también es un abierto. la unión arbitraria de elementos en tau, es también un elemento de tau. Okay, so this is closed then, tau is closed under finite intersections and closed under arbitrary unions. All right, and for functorial purposes, I will denote tau by d of x, okay? Tau and d of x is the same. All right, and this is a canonical example that will motivate the definition of frame, actually. This example is paramount. Okay, what's this special frame L? A frame is special when the frame L is D of X, so is the set of open sets of some topological space. So, and we will see later that, in fact, every type of frames are always special. And that's very important because then we are characterizing on a different context topology space. So we have here topological spaces. We can study within topology, but then here we have some algebraic concepts. In fact, we have lattice concepts. And in this context, we can study that topological space as long as we find a functor between these two categories. All right. What's an algebraic frame? Algebraic frame is a complete lattice L in which every element can be expressed as a supremum of compact elements. Okay. This is the hot part. My objective is to define a topology on spec of L. That is in the set of all prime elements of a frame L, of lattice L. I will define for every element A in F, and I apologize, this should be L. I don't know, it was a lapsus. Esto debería ser L. Es un error mío. Tal vez lo puse F por frame. Okay. U of A is the set of all primes such that these primes do not contain A. Do not contain A. I prefiero explicar bien qué se refiere este UDA porque estos son muy importantes. UDA son todos los primos del retículo L que no cubren a A, que no lo cubren. Es decir, A no es menor o igual que B. Okay, and now we are very concerned about the UAs, but with A not an arbitrary element of L, but a compact. A compact. And we will prove that this is an open base for a topology on spec of L. And this is the so-called Pearl kernel topology, also known as Zariski topology. Okay, before developing all the machinery, we need two lemmas. The first one. Why do I have here? Okay, because earlier we had the first one. Okay. If L is an algebraic frame and K is a compact, this set has a maximal element. And this maximal element ends up to be prime. Okay. I don't think I will have the time to go over the whole proof, but this is based on Zorn's lemma. Zorn's lemma will just take care of this truth. So we take, Zorn's lemma takes considers a partial ordered set, and if any chain has an upper bound, then that set has, if it has an upper bound in the set, then this set has a maximal element. All right, this is the proof. It's a standard Zorn's lemma proof. This is, I would say, this is very cool because this is in the context of just lattices. Okay. The second part of this proof is specifying why this maximal element M is prime. And it's not difficult to show it. Okay, next, lemma 3. The infimum of all prime elements is 0. El conjunto, si consideramos el conjunto de todos los primos, y tomamos el ínfimo de este conjunto, es 0. 0 no es un primo, por si acaso. Ok. Y 0 no es un número, ¿verdad? Es el elemento inferior de todo un retículo. Podemos estar hablando de, aquí por ejemplo, el vacío es el 0, ¿verdad? El elemento que está más abajo. Ok. Suppose that it's not 0. That means that it's greater than 0. Nothing can be negative, right? We're talking about lattice and a partially ordered set, of course. Then there exists C such that this inequality happens because since the lattice is an algebraic lattice, this element C is the soup of compacts, and then we have this, since it's compact, we have this chain of inequalities for all i's, and this means that at least one of the compacts must be positive, and then we have this other inequality. And then this SK, because of the previous lemma in which we said that the infimum of all primes is 0, we have this this inequality. I'm sorry. Oh, no, my bad. Because of lemma 2, not because the infimum of all primes is 0, but because it has a maximal element, SK will have a maximal element, and let's call it P. And by the same lemma, P is prime, and therefore we have this other chain of inequalities. So P must be in SK, or must not be in SK, but this contradicts the fact that P is in fact in SK. All right. So again, we have the same definition of the use of A's. I'm just recalling this because this is so important. This is crucial. This is the main theorem. So we consider L to be an algebraic frame, and we say that all these statements are true. Este es el teorema más importante. U de 0 es el vacío, U de 1 es todo el conjunto de primos. La intersección es cerrada. La intersección, o sea, la intersección de elementos de los U sub A es cerrada, eso es lo que estamos diciendo. Esto es la propiedad de la intersección finita de abiertos de una topología. Y esta es la unión arbitraria de abiertos, que es cerrada de una topología. So, this is very biased, I would say, because here we are pointing, okay, we want to construct a topology. We want to construct a topology. So, 1, 2, 3, and 4 are key ones. The last one is just to let you know that there are more properties that are very nice ones for this set of that we will call open sets. Okay, the proof. I think it's worth to go over the proof. So how do we show that U of A is empty? Well, if U of A is empty, then A is 0. Suppose that, well, U of A is the empty set, then what's U of A? I will write it down here. Para no estar retrocediendo cada rato, voy a escribir lo que es U. U de A es el conjunto de todos los primos. Eso hemos dicho. Spec es simplemente denota el punto de todos los primos, tales que no cubren a A. No cubren A. Recuerden que estamos en un retículo. La tricotomía no se da. Puede ser que dos elementos sean incompatibles. Okay. Okay, so if it's empty, it means that this never happens for every P. So A will always be less than or equal to B. So that's the negation of this. So that's what we have here for all P. Oh, but we know that the infimum, by lemma 3, we prove that the infimum of all primes is 0. So A is less than or equal to 0. But the only element that is less than or equal to 0 is 0. So we have that A is 0. What about assuming that well, if P is in the spectrum and P is greater than 0, then obviously well, not because not if we are given, but we know that all primes by definition are positive. So P will never be less than or equal to 0. So that's why U of 0 is always empty. Condition 3. Let me go over this one because in the other one we have. Let me go back. Aquí tenemos dos propiedades, la 3 y la 4. Cerrado para la intersección y cerrado para la unión arbitraria. Por el tiempo, permítanme probar una sola. Allow me to prove just one of these because of time constraints. So I think it's more understandable, this one. Let me show it to you. So we take a P in, and I'm doing this for you to have a taste of how the proofs look like. Hago estas demostraciones, no debería tal vez hacerlas en una charla, pero para que vean el sabor de cómo es la teoría de retículos aplicada a topología. Okay, so if we will prove this the equality as an equality of sets. So let's take a prime in the intersection. This is if B is in the intersection, then A is not less than or equal to B. So there you go. If B is in U of B, so if we replace B here, then B is not less than or equal to B. That is right there. Well, now I will prove this kind of saying by the contrapositive. So assume that P is not, well, by means of contradiction, I would say, suppose that P is not in U of A infimum B. If it's not there, si el ínfimo de A y B no está aquí, entonces la negación de esto se cumple, es decir, A ínfimo B es menor o igual que B. So we have that here. A infimum B is not less than or equal to B, but B is prime. We have defined a prime number this way. A is less than or equal to B, or B is less than or equal to B. That is a contradiction. because that was exactly our hypothesis. So we have this inclusion. The other inclusion happens because, and now I'm using the contrapositive, if we follow this implication, if B is not in U of A in U of B, it means that P if B is not in U of A in B, that is the set of all kinds such that A in B is less than or equal to B. So if it is not in here, then A in B is less than or equal to B, right? All right. So so I would have this negation, right? And therefore, A is less than or equal to P, or B is less than or equal to P, and therefore, and I made a mistake here. This should be, cometí otro error aquí. Esto debería ser U de A, intersección U de B. He cometido un error. Ahí es P, not P. Entonces, me he equivocado. Esta primera línea, this first should be U of A intersection U of B. And this means that P is in the complement if you want. And this means that, well, this set is equal to U of A complement union U of B complement. And this means that P does not belong to U of A, or P does not belong to U of B. And this means that P covers A and B is less than or equal to P. That's what I have here. Okay, now this is very clear. Sorry about this mistake. So we have this happens. Oh, but if we just take one of these two, the infimum is always less than or equal to A, and also less than or equal to B, right? El infimo de dos elementos siempre es menor o igual que cualquiera, es una cota inferior. And therefore, we have this one. So P is not in U of A infimum B, and there we go. All right. The proof of la prueba de que la unión la unión arbitraria de elementos de la forma UA es cerrada, funciona, it works this way, funciona de esta forma. It's straightforward, es una demostración directa. Ok, la demostración no está hecha en este orden. He probado primero 1 y 2. Perdón, no he probado 2. I did not prove 2. He probado 3 y 4. Y al final voy a hacer la 2. Aquí está la 2 recién. So, U of 1 clearly is the set of all primes, because no prime can exceed 1, right? And because L is an algebraic frame, 1 is the supreme of all compact elements. So we have this chain of equalities, and this shows 4. Straightforward. Okay. Now theorem 5. This is the central theorem. Es el teorema central. Porque aquí definimos la topología. We consider this space what is a base of for a topology? ¿Qué es una base de una topología? Una base de una topología es un conjunto, una colección de subconjuntos de X. Si queremos definir una base para el espacio topológico X, es un subconjunto es una colección de subconjuntos de X que es cerrado por la intersección, de dos elementos y cerrado para la unión arbitraria de elementos de esta colección. Y además, el vacío y X tienen que estar en esta colección. Esos son los tres axiomas de topología, ¿verdad? Perdón, esos son los tres axiomas. ¿Y qué es una base? Una base simplemente es un conjunto de colecciones que es cerrado bajo la intersección y que la unión de todos esos tiene que ser todo el espacio. Okay, so after recalling what is a base, I will define the U of A's, but with some particularity. A is compact. O sea, tomo los U de A's, pero con la característica de que A es un compacto. Hemos definido lo que es un compacto, ¿verdad? A es un compacto si A es menor o igual que el supremo de elementos arbitrarios, o sea que si tiene una cubierta abierta, entonces un cubrimiento abierto, entonces tiene un subrecubrimiento finito. Eso es un compacto. Okay, so we restrict the U of A's to compact elements. And this becomes a base for the spectrum of error. And in fact, furthermore, más aún, the open sets of this topology are precisely the elements of this form. Los abiertos de la topología que estamos construyendo van a ser exactamente de la forma UDA. O sea, cualquier abierto del espacio X que estamos construyendo va a ser de la forma UDA para algún A compacto. Okay, and this topology is called the whole kernel topology. A esta topología se le llama la topología envoltura núclea. No he encontrado una traducción. En inglés es whole kernel topology. Whole significa envoltura y kernel, ustedes saben, como grupos, el kernel de un grupo, whole kernel topology. Okay. The proof of this theorem is just using 1, 2, 3, and 4 of the previous theorem. On top of that, we have that indeed is, well, not on top of that, but so this collection of sets is indeed a base for a topology on spec of error. Okay. I will denote F, R, M, and TOP, the categories of frames and topological space. Sorry, lo siento por los errores aquí. Denotamos por FRM a la categoría de marcos y top a la categoría de espacios topológicos. Okay, and this theorem is what I was explaining before. Este teorema es como, presento mi documento. Esto certifica que si hago construcciones topológicas sobre retículos, para crear espacios topológicos, entonces tiene que haber una conexión entre estas dos categorías. Y eso es lo que dice este teorema. O sea, este es el que da la certificación de que todo lo que se está haciendo aquí sirve perfectamente para estudiar topología. Si tienen ustedes un problema en topología, muy difícil tal vez en el contexto de topología, lo traducen a retículos y tal vez es más sencillo, tal vez es incluso trivial, como hay casos. Y este es el puente. Okay, this is the bridge between the category of frames and topology. How we express it? Well, we consider an algebraic frame L, and we will say that, then L is spatial. In particular, L is isomorphic to, and there is another type here. Here I should put, me he olvidado escribir aquí lo que dice. L es isomorfo a, oh no, está aquí. Está aquí, obviamente es un salto de línea. L is isomorphic to D of the spec of L via this mapping. To every X in L, we assign U of X. You know what U of X is, it's right there. Okay. For example, since we have these translations, we can characterize compacts in L. If C is a compact in L, then U of C is a compact in the space, in the prime spectrum, in the topological space, for example. Okay. What did I do here? I think I jumped. Okay, I'm fine. Okay, we defined X and Y, and okay, there we go. 0 and 6 is, I don't know what happened to me. Nuevamente, disculpen, cuando dije que este es el certificado de que me permite que haya un puente entre topología y marcos, es este. So, and this works as follows. X and Y are topological spaces. We consider a continuous function from X to Y. The function d of f defined by this way. So to every y, to every open in y, open u, we define the inverse image of u under f. And you know, ustedes saben que si f es continua entre dos espacios topológicos, entonces la imagen inversa de un abierto es abierto. Esa es la definición. That's the definition. So this is perfectly well defined. So this becomes a contravariant function. Okay, and there is an inverse function that to every if we have two frames, then we can a homomorphism between two frames. Then we can define an isomorphism or homeomorphism between two topological spaces. So that's why we have that this is there is a direct connection. Hay una conexión directa entre la categoría de espacios topológicos y marcos. Okay, in particular, we have this that every algebraic frame L is spatial. Okay. I will go over a couple of applications. Dos aplicaciones. The way we have constructed a spec of L, in the same way we can construct max of L, the space of maximal ideals. ¿Qué es un ideal? En teoría de anillos, definimos lo que es un ideal en anillos de una manera muy sencilla, ¿verdad? Pues si tenemos un anillo R, a ring R, and a sub-ring, un subanillo de R. Cuando un subanillo, cuando este anillo es un ideal. Si consideramos R en R y digamos A en I, entonces RA, vamos a asumir que R es conmutativo. Esto está aquí. That's the definition of ideal, right? What is the definition of ideal in the context of frames? ¿Cuál es la definición de Ramiro, perdón, de ideal en el contexto de retículos? Si tenemos un retículo L y consideramos un subconjunto I del retículo L, si consideramos X en L y un A en I, entonces X y en fin, lo que considera R, ¿no? Ya, está bien. Sí. X ínfimo A está en I. Esta es la definición de ideal en el contexto de retículos. Y todos los teoremas funcionan muy similarmente. Every property of ideal theory happens in ideals in lattices. For example, all maximal ideals are prime. Todos los ideales maximales son primos. Eso sabemos de teoría de ideales. Y lo mismo pasa aquí. Todos los ideales maximales son primos. ¿Qué significa primo? Si tomamos este conjunto, son todos los X de L, tal que X está por debajo de A. Este es un ideal principal. En teoría de Niels se lo denota de esta forma. If we consider, for example, in frames that an ideal is maximal, then the ideal is prime. Okay, and it's prime when A is prime in this case. This particular ideal. Okay. Un ejemplo. One example. In topology, topologists are very concerned about some examples. Los que hacen topología en su investigación quieren buscar, su tarea es encontrar espacios topológicos muy particulares. Y, por ejemplo, encontrar espacios cero dimensionales. Es muy importante. ¿Qué es un espacio cero dimensional? Es un espacio topológico que tiene una base de subconjuntos que son abiertos y cerrados a la vez. A eso se llama closed, por las palabras en inglés, closed, open, abierto. Bueno, y no había muchos ejemplos de espacios cero dimensionales, eran muy raros, difíciles de manejar. Si definimos el espacio de ideales maximales, este resulta ser, perdón, si tomamos un álgebra de Boole completo, entonces su espacio de ideales maximales es cero dimensional y además es Hausdorff. Este, por ejemplo, fue un gran resultado, porque les permitió a muchos topólogos encontrar, o sea, salió esto y es decir, las siguientes semanas salieron muchos artículos porque tenían problemas para resolver, querían ejemplos de espacios topológicos de dimensión cero. Y salieron los artículos después de esto, pero se lo hizo en álgebra y salieron ganando los topólogos. Usaron eso y los topólogos publicaron mucho. Y hay muchos otros ejemplos de aplicaciones. Como les digo, para cada gusto del cliente topólogo, le podemos encontrar un ejemplo de un espacio del que necesitan. No en general, pero en muchos casos sí funciona. Y también problemas. problemas. Hay muchos problemas, por ejemplo, para encontrar la compactificación de un espacio, cómo se comporta. Con compactificación me refiero, si tenemos los reales, por ejemplo, el infinito no está ahí, pero podemos poner al infinito como parte de los números reales y definir intervalos abiertos que los contienen y construir una nueva regla, una nueva topología en los reales unido con el infinito, y eso se llama la compactificación de los reales. En general, para espacios topológicos se hace la compactificación y utilizando marcos es más sencillo, mucho más sencillo. Y nuevamente ahí los que más se benefician son los topólogos. Muy bien. Thank you. Eso fue todo. Muchas gracias.